Hey everyone, just a real quick update. Hopefully you've taken your quiz by now, okay? And pretty much this is kind of a busy week, so as quick as you can, try and watch this complete video, okay? And in the video, I tell you all the details you need for those two labs which are due this week, okay? So watch the video through, pay close attention to material relating to your labs. Maybe worth a quick peek at the lab before you read this, or watch this rather. Okay, and then as you go through, you can just kind of make a mental note of the kind of the theory you need, and that should cover everything for your two labs this week. It's kind of a busy week, okay, just because of the way the syllabus is, but try and look at this as early as you can. And then the lab, I did have one due on Friday and then one due on Sunday, so I extended the deadline for the second one. Okay, and also in the lab, I just did actually go through it recently just to kind of upgrade it for this semester. And we're not doing the carbonate lab. I mentioned the carbonate lab a couple of times and give examples. We're not doing that lab this semester. We're doing the two this week instead. So, I do mention that in there. So if you kind of, what's he talking about with his carbonate lab, that's actually an old lab, and, so we're doing different ones. But the theory is still the same, okay? So the theory for the carbonate buffer is, the same that works for every buffer. So, yeah, still relevant. Okay, stop there. Roll video. Okay, welcome to the acid-base Equilibria 3 packet. When I get here in the notes, I'm often reminded of an interesting occurrence that happened some time ago now. I'd been teaching chemistry for about 5 years at JJC, and I had 3 very alarmed pre-meds come to my office. And Dr. Mills, you've got to tell us about buffers. And buffers are traditionally a tricky topic in chemistry 102, but how we like to think about it is not as a separate topic. And if you get this kind of idea straight, it's not so bad at all. Buffers aren't a separate thing, they're just an application of the ICE grid. Okay, so we're going to tinker with the grid a little bit and we'll see how buffers work. A buffer is essentially a solution that resists changes in pH. Okay, so we'll look at that as we go, but we need a little bit of background first. Okay, so this is all parts of, additional aspects of acid-base equilibrium. The next couple of pages actually really help with your carbonate lab. So if you're here before you finish that carbonate write-up, good news, right? So I'll give you a bit of extra info. All right, so salts and polyprotic acid. Salts. Okay, I should say really a salt of a weak acid, right? So if I mix you, for example, sodium hydroxide and acetic acid, what do I make? I make sodium acetate, right? Sodium acetate is the salt of a weak acid and a strong base. There it is. Okay. Now, if I dissolve that in water, what do I make? I make the separate ions, of course. This is actually reminiscent of your carbonate lab, isn't it? Because that was also sodium carbonate, which is the salt of a weak acid. Okay, so somewhat similar there. All right. So there we go. So we have the conjugate base of a weak acid produced, if you like, by itself. All right. So that's just sitting there in solution with sodium, not H+. All right. So we've got a kind of a base by itself in solution. All right. Now, equation 1, what would you expect to happen? And again, very similar to the lab. I showed you this in the pre-lab if you want to go back and remind yourself. Okay, what would happen? Would you expect this solution to be acidic, basic, or neutral? If you remember the carbonate lab, it was basic. Okay, so it's kind of a small detail for your lab because we essentially ignored it when we did titration math. Okay, but it was basic to start. It started our titration at pH 10. Okay, so what happens is, of course, the weak conjugate base we've just put into the water reacts a little bit with the water because it's a base, right, to make undissociated acid and OH minus. Okay, so the solution of that, the pH of that solution will be basic. Okay, probably somewhere between 7 and 10 at a guess. Okay, so there's our second equation and there's our first equation. Okay, so two equations. The initial dissolution to make the conjugate base, if you like, by itself without any H plus in solution, and then that reacting with water to make OH minus. Okay, now this is a modified ICE because we're dealing with bases. Okay, we just put a base into solution, and I've been a little tricky here because examiners love to be tricky, right? Okay, they give you Ka for the weak acid, okay, but we have the conjugate base in solution, so what we need is Kb. Okay, this equilibrium is governed by Kb because it's the conjugate base reacting, not the acid. Okay, so be careful there. First, remember the golden rule: Kw equals Ka Kb. Therefore, Kb equals Kw Ka, which equals 10 to the minus 14 over 5. Sorry, 1.8 is up here. 1.8 times 10 to the minus 5. Now it comes out to 5.56 times 10 to the minus 10. So be very careful there. If you're given a conjugate base from dissolving a salt of that conjugate base in solution, Kb governs that equilibrium because it's a base reacting. Okay. We like to kind of quote Ka values in the back of the book because it's a bit like pH, right? We talk in terms of acid, but sometimes we need to think in terms of base. So pH, POH, Ka, Kb. All right, now to the question itself. Pull this up. So Kb equals products over reactants. Oh, I should read the question, right? Calculate the pH of a solution made by dissolving 10 grams of sodium carbonate, i.e. this process happens, in water making the final volume 1 liter. Okay, so products over reactants. You could write Na C2H3O2, or you can just put the anion. Okay, so that's true, isn't it? Okay, which equals, and you know, I'm going to resist the temptation to draw the grid out again. Okay, we understand on top it's going to be x squared, right? Now, what's on the bottom is the concentration of. Actually, I will do the grid on the side over here. Okay, actually, on a separate piece of paper, I do the grid. Right. So. C2H3O2 minus plus H2O, boom. You know, that's our first one, so we do the grid. Yeah, as you get familiar with this, you'll just knock out the, the x squared on top. But there it is. So ICE. Initially, well, we've got 10 grams, and I'm going to tell you the molecular weight is 82.0 something, right, grams per mole. So you divide that out, you get 0.122 moles, and it's in 1 liter. So it's the same strength, mole per liter, mole in a liter. 0, 0. So it's looking very familiar, but it's a base, not a weak acid, right? Okay. So then, change, minus x, plus x, plus x. Weak base approximation. Minus x is the same number because it's the large minus the small. X and x. So therefore, Ka, oops, okay, did it, didn't I? Kb equals products over reactants, which is where we were. Okay, so that's where we were. So x squared over, remember what I just had, 0.122. All right, so Kb, 5.56 times 10 to the minus 10 equals x squared over 0.122 x, which equals OH, equals, this times this square rooted. Which equals, we can get the number here, 8.2 times 10 to the minus 6 moles per liter. That's the concentration of OH minus. So POH minus log of 8.6 times 10 to the minus 6. Running out of room, apologize for that. Let's just do that real quick. Let's get the calculator out. So 8.6 10 to the minus 6. And find my log function. 5.5. Okay. Let's make sure you get the same thing there. Let me just make sure I did that right. .2 10 minus 6 log, yeah, 5.5. So pH, let's go up here, 14 minus 5.5. Should do that in my head. 8.5. So that makes sense. The pH of this solution, and you know, with rounding, you might get a slightly different number, but you got the idea there. Okay. So with a base, we expect a pH greater than 7, right? It's a basic pH, a little bit over 8.5. Okay. All right. So again, ICE grid. Hopefully that's actually quite similar. If you remember, I gave you that extra credit homework, right? Hopefully you've done that, right? Okay, it's similar to that. Okay. Next thing, so that's a salt, all right. Next thing, this really helps with our lab again. So what is the difference between a monoprotic and a polyprotic acid, right? Well, mono means one, right? One what? 1H plus formula. For example, HCl. HCl is a classic monoprotic acid, right? So poly means more. You can have di, you can have tri even. So an example of a di would be 2H plus. The classic is, of course, H2SO4, or your lab, H2CO3. Okay, carbonate, iron, -2, 2H pluses, carbonic acid, and then sulfate, -2, 2H pluses, sulfuric acid. Tri, there's only one real good one. Well, actually, there's a few out there. Citric acid actually is triprotic, but the classic is phosphoric acid. Okay. Now, we're not going to go through the math of this in great detail now. We'll actually come back to this piece here when we talk about something called half equivalence, right? So if you want to keep that phrase in your head. And this is the answer to the pre-med question. Half equivalence is how you work out the pH of a buffer, okay, which we'll talk about later. But that is a titration curve for a diprotic acid. Now we're starting at pH low here, so we're starting with the acid intact. So H2CO3, for example, this is generic, right? But this could be carbonic acid, right? You titrate it, you get that first inflection point, and then you titrate it and keep going to get that second inflection point. That looks very similar, doesn't it? But kind of upside down to what we did with our lab. In our lab, we kind of went the other way. So we started at a high pH because we started with carbonate, not carbonic acid. So we're titrating with H plus, not OH minus. So we got the kind of the flipped upside down version, if that makes sense. Okay, and those are your 2 points of inflection. So, you know, I'll flip that upside down. Kind of looks the same, doesn't it? Okay. All right, so that's the titration of a diprotic acid. That would be with a base, obviously. This is your lab, the titration of a basic conjugate over here with an acid. Okay, so you know, that's the general shape. We'll get back to the math again, you know, what these points actually mean in more detail in a little bit. Okay. Now, in your lab, you know, so obviously we didn't do this in practice. And to be honest, I mean, it's one that doesn't hurt so much from not being there because, you know, as long as you understand how that pH probe measures, you know, obviously the pH as the titration goes on, it generates the curve for you. But of course, back in the day, okay, we didn't have pH probes, okay? we actually used indicator. Okay, and there's the classic right there. There's the classic phenolphthalein. Phenolphthalein is used a lot because it goes from colorless to pink, right? The human eye is really good at seeing something and not something. So pink or not there is a good indicator. There are other indicators available, and there's many, many of them, okay, which change from one color to another. It's hard to see with the human eye a gradual change in color. So we tend not to use them. We tend to use only really the one that's on or off, okay? But hey, let's pretend we don't have a pH probe, okay? We don't have a pH probe. Which indicators from, you know, the available list would be best for detecting the two titration endpoints in the previous titration? What endpoints would you see? Okay, so we're looking here, right? If we look, we have an endpoint at 11.9 and an endpoint at 6. So we see the endpoints from our, you know, from our more sophisticated technique with the pH probe. We see those endpoints, right? So, you know, back in the day, what we do, we'd pick something that changes at 6 and something that changes at essentially 12, right? So what would be a good choice? So look down here, what changes at 6? That's done by 6, right? And that's kind of yellow at 6. Now think about what we're doing, right? We're titrating. Go back to the picture. We're titrating in a more basic direction, right? Sorry, we're titrating in a more basic direction, yeah. So we want something that changes as the number gets bigger, all right? So it starts just before 12 and finishes after 12, if that makes sense. It starts just before 6 and it finishes after 6. Have a look. Why don't you pause right now, take a look at that little list there, and say, hey, which one am I going to choose? Well, I'm going to choose bromol phenol blue, right, which changes at 6 to 8, or I could possibly, because it's actually probably a better choice actually, that one, methyl red, right? So either of these would probably do. I think I'm erring towards methyl red as a better one, right? Because it is red below 6 and yellow above 6. This one changes to yellow, bromol phenol blue changes, it's yellow right at 6, so we might miss it actually, so this is the better one. All right, now, and so that goes from what? It goes from red to yellow. All right, now, what's another good choice? Something that changes just before 12. Well, there's only really one, isn't there, right? It's azurin yellow, right? Azurin yellow down here. Sounds very Harry Potter, right? Azurin yellow. Sorry, alizarin yellow, which goes from yellow to red. So the question says, what would we expect? Well, at the low pH range, this guy's yellow and this guy's red, right? So there's two things in the beaker at the same time. This will go to yellow, so it'll go from red to yellow. This will still be yellow when we get to pH 6. So we'd see a red to yellow for endpoint 1, okay? And then yellow to red for endpoint 2. So as we titrate this, it will start red. We stop when it turns yellow. Keep going, it'll turn from yellow to red, stop again. Those will be those 2 points of inflection on the graph. Okay, so if I draw that here, okay. Red to yellow, yellow to red. Okay. Oops, sorry, there we go. Red to yellow, yellow to red. Okay, that's what we used to do back in the day. Now, if you think about it, we've seen kind of you have to combine the two colors of the two indicators there. So for some hardcore extra credit, universal indicator paper. It changes color gradually as you go from very low to very high pH, right? So it has a multiple number of these things in it. Okay, it's kind of a closely guarded secret what they actually put in there, but you kind of figure it out, right? So if you think about it, you know, which of these would cover all the bases from pH 1 to pH 14, and we see, if you like, a distinct color of the indicator paper, hopefully matching, you know, you can make your own if you want, okay? Oop, turn it up. So what would the color of the mixture be at certain pHs 1 through 14, and which one of these would you need to do? Okay, so if you want to type that out and send it to me, feel free. Okay, that's kind of a tricky one. I don't really expect you to do that necessarily. It's just kind of a fun kind of thing if you're just looking for something to do. You know, how would I make my own universal indicator paper? That's the question, right? Okay. So next, so the common ion effect. All right, so this is kind of a big deal. It comes in many guises, so to speak. Okay, all right. So we go back to that acetic acid again. Okay, so let's pretend. Okay, so we have this stuff in a container, right? So you got the acid. I'll do a generic. Okay, it could be acetic acid. It could be some other weak acid. There it is sitting in solution. Okay, so according to Chatelier's principle, what would happen to this equilibrium if you threw some sodium acetate, for example, in there, right? So a lot more A- was thrown in. Okay, you don't throw any more H pluses in there, just this one. Okay, what's going to happen to that equilibrium? Well, you stress an equilibrium, it kind of does the opposite. It pushes back to maintain the equilibrium. So if I increase the amount of A-, it then turns it into reactant to reduce it. Okay, so you reduce the amount of H plus, you reduce the amount of A minus by turning these products into original reactants. Okay, so it moves, as we say, moves to left to establish the equilibrium ratio as it should be. Okay, so that's called the common ion, right? So that's the concept. Okay, if you have an equilibrium and you throw in something that's either exclusively on the left or right, the equilibrium will remove it. Okay, it will move in the direction necessary to remove the thing you just added. Remember, equilibrium is stressed, it will remove that stress. Okay, so get that concept in your head. Okay, you add a common ion, the equilibrium shifts to remove it. If you look this up in the book, and I hate this part of the book, okay, it's unnecessarily complex. That is what the book says about it, right? The extent of ionization of a weak electrolyte, in other words, how much ions I have over here, is decreased by adding a strong electrolyte such as a salt that has a common ion. So add this, it goes that way. Okay, so you know, don't get distracted by people with 10-cent words. Okay, this is really saying this. Okay, you throw a common ion in, the equilibrium shifts to remove it. That's all you need to know, and that is the fundamental basis of the buffering effect. Okay, because we can remove H plus, makes sense, right? So remove H plus, we'd maintain pH. Okay. All right, now here's a worked example. All right, let's go through this nice and slow together. Okay, so it's a common ion effect. It could as well be a buffer, right? It could as well be a buffer. So I think of this as a practice kind of baby buffer if you want, or just a common ion effect, all right? So what's the pH of a solution made by adding 0.25 moles of acetic acid to 0.75 moles of sodium acetate, enough water to make a liter? Okay, so there's our grid. They've already set it up for us, right? But let's do it ourselves, right? Because it's nice to practice. So we have HC2H3O2. So we'll all set up the base equilibrium of the acid, right? And then we're going to add a common ion, which is going to be the acetate ion. So there's our equilibrium, all right? Initial change equilibrium. Okay. Initially, let's get back to the question. It's going to be the same table we have there. Okay. It says, what's the pH of a solution made by adding 1.25 moles of acid? And it's in 1 liter, so it's the same strength, right? Normally we write 0 here and 0 here, right? And we can write 0 for that one, but, this is the big but, right? When we have the common ion, right, we're adding some acetate from sodium acetate. If you like, that's going to break apart completely, right? So we're going to have 0.075 moles in a liter of that. So that's what's new, okay? In a common ion problem, this initial line is not the same as it would be just for the acid dissociating, okay? You have an exterior source initially of conjugate base, right? So just knock that on top. All right. Then it's exactly the same procedure. Minus x plus x plus x. So what do we have? 0.125, yes, minus x, but weak acid approximation, right? X, and again here, we can do the weak acid approximation. X is tiny, so it's approximately 0.075. All right, nearly there. So up here, right, we can do that. And that's the true math, right? But because x is super small, it's not relevant. Okay, nearly there, right? So, therefore, great place to pause here, right? If you want to try and just stick it in the K math, you can. Ka equals products. Oh, products. Let me start that again. Ka H plus A minus over HA. Ka was given at the top. If you flip to the top of the page, 1.8 times 10 to the minus 5 equals, normally we write x squared, but we're not, because it's 0.075 times x, 0.075 times x, right, over 0.125. So therefore x, which equals h plus, equals 1.8 times 10 to the minus 5 times 0.125, and then divide by, I haven't got room to write it underneath, 0.075. All right, let's do that real quick. Can't seem to locate the calculator. Oh, there it is. Drama over. Okay, so 1.8 times 10 to the 5 minus, divided by 0.125. Sorry, oh, messed that up. 1.8 times 10 to the minus 5 times 0.125 equals, divided by 0.075 equals 3.0 times 10 to the minus 5 moles per liter. Okay. Therefore, pH equals minus log of H plus ion concentration. .5. It's acidic. Alright. Alright. So that's the pH of that, essentially what is a buffer solution, okay? And for details we'll talk about in a little bit. This solution will maintain its pH, alright? So when we have a weak acid and its conjugate base in solution, we can add a little bit of acid, we can add a little bit of base, and as we'll see, the pH is basically that's no pun intended, the pH is essentially maintained. Alright, so work through that one, nice and slow, make sure it makes kind of sense. Alright, now, my videos always have a time limit of half an hour, and we're rapidly approaching that. Okay, so in the next video, I'll start off by going through this question, okay? But what I want you to do is try it yourself, okay? Try this before you look at the next video. The answers are there, okay? This is a common ion effect, okay? So let's just set up the equilibrium. It's HF in equilibrium with H plus and F minus, but we're adding in some HCl, and HCl is a source of H plus because HCl is a strong electrolyte, right? So on the side we can write one single arrow. So this is the thing that's going to go up, right? Okay, so you can have initial change equilibrium. The initial condition, this will not be zero. Okay, so there's your little clue. Get started on that. I have 55 seconds to stop, so I'm going to stop. Alright, so let's look at this problem. Let's read it, and then hopefully you got the answer. The answers are given down here, okay, so hopefully you got that. Alright, but let's go through, let's check, okay. So, calculate the F minus ion concentration and the pH of a solution that's simultaneously 0.2 and 0.1 HF and HCl. And they give us Ka for HF, which is a nice clue. Oh, there goes my timer from before. Alright, so there's a nice clue that HF is the weak acid, so that makes sense. Okay, so initially 0.2 HF, 0 and 0 if it was just the weak acid equilibrium, right? But it's not, because we're throwing in some HCl of 0.1, and HCl gives us 0.1H plus, and that's 0. Okay, so slightly different. H plus is the common ion here. Change, minus X plus X plus X. Equilibrium, again make the weak acid approximation. And the question did say, what is F minus? F minus is X, right? So we'll solve for X in a moment, okay? And then the pH, okay? The pH is going to be straightforward, which we'll talk about last, because we know the concentration is 0.1, right? Essentially. What we could do, and we'll do it to compare, we'll throw in the amount of H plus that comes from the HF dissociation and see how much it affects pH. It won't affect it hardly at all, I think. Okay, so Ka equals products, 0.1 times X over 0.2. We should probably do that, right? Therefore, 6.8 times 10 to the minus 4 equals 0.1 X 0.2. Therefore, X, which equals, if you remember, F minus, the thing we want, equals 6.8 times 10 to the minus 4, 0.2 over 0.1, which equals 1.4 times 10 to the minus 3 molar. Okay, look down here. Yes, that's what we got. Now, pH is easy, right? pH, I'm going to put approximately identically equal to, the concentration of H plus is approximately 0.1, right? So it's minus log of 0.1, which equals 0.1 log, I should know that, 1, right? pH equals 1. What happens if we actually count in? It's not just that, it's, if we did this for real, right, it's actually 0.10 plus X, right? Okay, so the actual, if we wanted to do this kind of for the true amount of H plus there with the H plus from the HCl and the H plus from the, oh, let me just move that up, sorry about that. So the pH is 1 for 0.1 moles per liter, right? The actual pH is the minus log of 0.1 plus, there's actually an extra little bit from the HF dissociation, 6 point, oh, what was the number? Yeah, 6.8 times 10 to the minus 4. All right, so that is 0.1, 1, 2, 3, 6, 8. That's the actual concentration in, you know, everyday units, right? So obviously, you know, let's do the log of that. 0.10068 log 0.997. So to the third significant figure, it's different. Did we measure? No, we didn't measure the third significant figure, so it's the same. So that's your comment, okay? Negligible H plus from HF. Okay. All right, so that kind of proves that the weak, oh, move it up. Negligible H plus from HF, just that, right? Which kind of proves that the weak acid approximation is valid. Okay, so that's another way to show that. Okay, and there's one for our answer. All right. Again, any questions on this, feel free to download the note packet I'm doing right now, take a look at it in more detail, or ask a question of me or others at the discussion section. All right, now we move on to the legendary buffers. Okay, so as we mentioned, a buffer solution is typically a weak acid and its conjugate base in the same container, but you can have weak bases as well, so you could have a weak base with its conjugate acid in containers, okay? We can do both, okay, but we tend to concentrate on the weak acid versions, all right? This is, as we mentioned, and don't get intimidated by this at all, right? This is a very specific application of the common ion effect. We have both conjugate base and weak acid in the same beaker. Okay, so the one we just looked at, right? So the HF one and the acetic acid one we just did were buffer solutions. We just didn't delve into the math in any more detail, right? So it's something we've already looked at, and we're just going to talk about it in terms of how that solution would change if we started to mess with it in terms of adding H plus and OH minus. Okay, so Chatelier's principle applies, right? So we're going to have this in a beaker. So think of this in a beaker, all right? Okay, so we have HA in equilibrium with H plus and A minus, right? Okay, if we throw in some H plus from an external source, so we have buffers in our blood, right? It's actually a carbonate buffer, right? Which we'll talk about later. But if we got stung by an ant or anything with like that injects us with acid, yeah, it stings for a second, right? And then it goes away because the H plus introduced to our blood is then removed from solution. Okay, if it stayed there and built up to a significant level, it would kill us. All right. Okay, so our blood naturally removes external H plus. It actually also removes external OH minus if it gets into us. But in nature, H plus is a thing that's often found in stings, which makes sense. All right, so back to it. So if a large amount of H plus from an external source were added, what would happen? Well, remember this is in a beaker, right? This would go up, wouldn't it? Right? If the external amount of H plus went in, the amount of H plus would go up. What would the equilibrium do? It would react it away by turning these things into reactants. Okay, and that's how a buffer works. If you have H plus as a product over here and you throw H plus in, it gets removed. Okay, so H plus as a product will, you know, act according to Chatelier when you add extra external H plus. Fair enough. Now that's the easy one to understand. The harder one to understand is resisting base, right? So let's go back and look at a equation again, but with base, right? So there's my generic. Okay, now think about it. Oh, forgot to mention it. Should have written it down. In the top one, move to the left. Okay, to remove H plus. Okay, now back to the base. Okay, what happens when we add base in there? Well, remember, H plus and OH minus are both strong reagents, and they react together to make what? H2O. So we're actually removing H plus from the solution to make H2O when we add OH minus. So if this goes down, what we're going to do? We're going to make some more, right? How do we make more? We turn reactants to products. So it moves to the right. Okay? So that's how it works. When we remove H plus, we move to the left. When we essentially remove external OH, we react it away, and then we replace the H plus that was reacted away. It moves to the right. Okay, so the equilibrium will move in different directions depending on what the external source is. Okay, H plus or OH minus. All right. Now, if you think about it, if I've got more H plus than HA, I'll be better at one thing than the other. Okay, and that comes to buffering capacity. Okay, buffering only works until you run out of buffering agent. Okay, so if I run out of H plus, I can't remove any more OH minus, for example. Okay, so a buffer will resist changes in pH. It will keep doing what it does, removing external H plus, removing external OH minus, until it runs out of the thing it needs to remove those items. Okay, so the buffering capacity is usually stated as a straight concentration. If I got 0.1 molar H plus in there, I can do a 0.1 molar OH. Okay. However, we normally talk about it in terms of a ratio. Yeah. So if I've got conjugate acid to conjugate base in a 10-to-1 ratio, I can do 10 more of one thing than the other. Okay. So we have absolute amount and also ratio of the components. All right. Now, question is, you know, you can create a buffer to maintain any, well, within limits, any pH, okay? And to think about that, think about a titration, because when you do a titration, you change the pH rapidly when you have a strong acid, strong base. And if I do a strong acid, strong base, Remember, a strong acid and a strong base have negligible strength conjugates, so this math doesn't apply. If I do pH versus volume NaOH for a strong acid, we get that classic strong acid, strong base titration curve. And at the middle of that inflection is where it's equivalent. Okay. Now, real quick, this is kind of interesting because this range in which this happens is extremely narrow. So you could choose any indicator you want because they'd all change over this narrow addition of NaOH here. Okay, if we look back, I can find my little picture here. People have this idea in their head that, oh, we use phenolphthalein because it changes at pH 7. Oh, no, it doesn't. Phenolphthalein changes at pH 9. We use phenolphthalein because it goes from colorless to pink, right? Okay. Why does that not matter with a strong acid, strong base? Because the gradient's super steep. It doesn't matter which area of this really rapid increase I look at, it's going to change for any of the indicator pHs. Okay, so phenolphthalein is actually up there. Phenolphthalein doesn't change at pH 7, it changes at pH 9, right? So that's pH 9, but that's okay. That's okay because it's in this steep change here. Okay, now when we have a buffered solution, all bets are off essentially, right? It's kind of really interesting what happens. So when we have a buffered solution, remember, let me draw you the graph first. All right. A weak acid, so I'm going to have conjugate, right? So it's going to have conjugate in there. So I've got HA, A minus, right? So there's going to be acid in the solution to start. It's going to have a lower pH to start, okay? And then we'll start to react as normal, but then we get what we call a buffering region, okay? In the buffering region, we're adding NaOH, yeah. So OH is coming in, reacting with this to make water, and then this is replacing it, yeah? Okay, so it's moving to the right. So in this region here, we're replacing the H plus that's reacted away with more H plus. So the pH stays approximately constant because the amount of H plus is approximately constant. We call that the buffering region. Okay, so it's like a flat part of the curve. And then it just goes crazy when it runs out of HA. When this is gone, it just turns into this curve. Okay, so if you think about it, it is that curve, but with this extra kind of buffering region. All right, hopefully that makes sense. Okay, so we'll always have a flat region of the curve in a buffered system where pH is approximately constant across a large change in external NaOH concentration, or in this case, if we did the other one, external H plus. All right. There's an example of the two curves together. There's the classic strong acid, strong base. There's the buffering region for a weak acid, strong base. Okay. All right. Now, in order to find, and this is that question we're going to get back to the previous page on. Okay, remember those students that came into my office and wanted to know what the pH of a buffer was? Well, it's kind of easy, to be honest. Okay, and once I told them the secret, they were like, oh, that's easy. Okay, so here are some buffers. Okay, they're all weak acid buffers. Okay, so there's our strong acid, that might be HCl. And then a stronger, a weaker, and then the weakest weak acid. So we see the Kas go from a reasonably large value for Ka to a super small value. Okay, now if you look, let's pick maybe this one here. Okay, the buffering region seems to go from pH 5 to pH 6, right? That seems to be the bracketed region there. Okay, and then right in the middle, actually goes slightly above 6, right in the middle is kind of the average, isn't it? So if we go there, let's read it, okay? Diagram illustrating the buffer region for weak acids. Okay, what do you notice about the relationship between Ka and the natural pH? All right, so here, pH equals 6, pKa equals 10 to the minus 6. Oh, look at that. Oh, sorry, Ka. Ka is 10 to the minus 6. I had a bit of a Freudian slip there, if you see what I'm doing. Okay, so the pH of the buffer is 6, and the Ka is 10 to the minus 6. What's pKa? Minus log 6. Ah, so right in the middle, halfway along the buffering region, right in the middle, the pH equals the pKa. So if you want a buffer of pH 6, choose a system with a Ka or a pKa of 6 as well. Okay, so pH equals pKa. That's the trick for the free meds. Okay, pH, pKa, well, approximately a buffer. Okay, so right in the middle of that, it'll change a little bit, but right in the middle, it's true. Okay, so pH equals pKa. We'll do a little bit of illustrative math for that in a second. All right, then we'll flip back to that other question. All right. So our first, if you wish, true buffer question, right? Okay, I'm probably going to set something pretty similar to this on your final midterm, all right? So buffers are essentially weak acids or weak bases with their conjugates. Use an ICE grid. Use an ICE grid. We're going to modify it just like the way we did with the common ion. All right. So find the pH of a buffer that's 0.12 lactic acid and 0.1 sodium lactate. Okay. So lactic acid, HC3H5O3. Yeah, that's the stuff in your muscles, right? When you work out. Okay, there it is. Like a grid, ICE 0.1, 2, 0, and then, hey, we got a sodium lactate, so same concentration of lactate ion initially. All right, so that's our initial setup, right? Change, usual thing, minus X, plus X, plus X. Apply weak acid approximation on the fly. Okay, so actually the math turns out easy because it's now x squared now, right? So Ka is H plus that okay, which equals H plus is X times other product 0.1 over 0.12. Ka is of course given 1.4 times 10 to the minus 4. Oh, move it up. Okay, need that Pavlovian bell, right? Okay, so just catch up there. So products at equilibrium, reactants at equilibrium. Okay, so therefore X, which equals H plus, equals 1.4 times 10 to the minus 4, 0.12, 0.1, which equals, do that math, 1.7 times 10 to the minus 4. So pH minus log of HF ion concentration, that number, 3.77. So that buffer will maintain a pH of 3.77. Oh, move it up here. Sorry about that. That buffer will maintain a pH of 3.77 when you throw an external H plus or OH minus. All right. Now, some interesting math. I'm old, that's an old group, but a cool group. That's the verve, right? Okay. Now, drugs are typically either weak acids or weak bases, right? So when you have something like aspirin or anything else you care to even think about, any kind of drug either has a carboxylic acid group on it or a nitrogen somewhere, which would make it a weak base. Okay, so drugs are typically weak acids or weak bases. So their equilibria are affected by this math. Okay, that's why it's such interest to MCAT and PCAT examiners. Okay, so drugs, it's important. If they're soluble, they can be taken as a tablet. If they're not soluble, they have to be injected, right? Okay, so of super relevance and importance. Okay, now on the MCAT and the PCAT test, there's loads of questions about buffers and pHs and things like that because of the relevance to drugs. Okay, so the question is, do you think they, i.e. the examiners, expect you to do a big old ICE table like we just did? The answer is obviously no, right? There's a trick. Okay, so we'll do a little bit of a derivation and show you a really nice equation. Okay, it's called the Henderson-Hasselbalch equation. I just call it the HH equation. Okay, literally anybody with a 200 or 100 level algebra can do this, right? Okay, but when a biochemist does it, apparently it's cause for a celebration. Okay, so let's show you what they did and how they pat themselves on the back so hard when they got this equation, and then how actually simple it is. Okay, so what we need is a relationship between pH and pKa, just like we saw with the previous graph. Okay, all right, so Ka equals H plus A minus over HA, our standard equilibrium expression, right? Okay, so eventually you want pKa, right? So why not take the log of both sides? Okay, log of Ka equals log of, and I write this slightly differently. I want to get H plus on its own eventually, right? Because minus log of H plus is pH. Okay, now, real quick, the log of something times something is the logs added together, right? So log Ka equals log of H plus log of A minus over HA. We're nearly there, folks, because remember the minus log is that p function, right? So just multiply everything through by minus. Minus log of Ka is pKa. Minus log of H plus is pH. Minus log, we're adding a minus, plus you have to excuse the background noise. I live in a house full of other people. Right. All right, so there it is, okay? So that's the Henderson-Hasselbalch equation. Pat yourself on the back. Very good, right, biochemist. But don't get ahead of yourself. All right, let's modify that. There we go. So there it is, okay? That's the relationship between pH and pKa. Now, that half equivalence thing, if you remember that graph, right? Let's go back. Try and find it. Excuse me, just rustling around here, right? So pH equaled pKa exactly halfway across the buffering region, right? That means you've used up half of the HA to make A minus, essentially, right? So think about that. If I had 100 HA to start and I use half of them up, it turns into 50, right? And I got 50 A minus at that point, right? So these numbers are equal at half equivalent, equal at half, what we call half equivalence, right? So hey, any number divided by itself is 1, log of 1 is 0. So at half equivalence, halfway across that buffering region, pH equals pKa. Because the slope on that graph wasn't so great, we can always say, hey, pH is approximately pKa, right? Because it's not such a big height difference, if you like. All right. Okay, pH equals pKa at half equivalence, but if you want the details, if you want all the extra, you know, significant figures and all that, that's the equation you would use. So let's go back and let's do that equation, okay? Again, let's do it again, but this time using the Henderson-Hasselbalch equation, all right? So it's the same question as before, right? And we got 3.7 or whatever it was, all right? So it was this one, right? So we did it just a minute ago, our first proper one. We got 3.77. Let's just throw it into the Henderson-Hasselbalch equation, right? So what's the pH of a buffer Okay, so pH equals pKa, all right, minus log of 1.4 times 10 to the minus 4. Minus log is the p function, remember? Plus the log of A minus, which is the acetate, over the acid, 0.12. All right, throw in the numbers. 3.85 plus negative 0.08. 3.77. Oh, there. 3.77. That's what they want you to do on the PCAT. Okay, so use the Henderson-Hasselbalch equation. As long as you have the ratio and the Ka, you can always work it out. Okay, so that's a nice shortcut. Nice shortcut. Now, real quick, got a couple of minutes left before the buzzer goes off. Back to that page here. If we look, halfway along, I've used up halfway towards the equivalence point. Halfway is here, so that's half equivalence. So that's pKa1, right? At pKa1, we have that number. pKa equals pKh at that number, right? So pKa is 2.3 Ka. Do the math. Just find the page in my notes, do the reverse math, so to speak. So 10 to the minus pKa, if you do that math, 5.0 times 10 to the minus 3. Down here, similar kind of deal, 10 to the minus pKa. I apologize for rushing, my buzzer's about to go off. 10 to the minus 10. All right, so bottom line is, because I knew pKa at half equivalence, Ka, pKa, remember p is take the minus log, okay, so 10 to the minus Ka would be the reverse, okay, pKa would be the reverse. All right, stop there. I've got 1 minute, 40 seconds until the buzzer goes off. Next video, video 3, we'll start talking about this whole half equivalence thing in a little bit more detail. Okay, so I've given you a brief kind of guide there of how that works. We'll meet that concept and we'll formalize it. Okay, and we'll get to the point where we make our PCAT friends happy. All right. Okay, let's stop there. All right, so we're back. Before we continue, a quick correction or two. Okay, I'm getting a little bit stir crazy here. That was actually 5.1 on the first page, and that made that 8.9. That was actually visible on the calculator, and I wrote 5.5 instead of 5.05. And you know, it's actually 8.9. Okay, moving through real quick. Also, when we did the Henderson-Hasselbalch, guess it's trickier than I thought, right? Down here, minus times a plus is a minus. Okay, then you rearrange that and you get the classic equation we used on the next page. Okay, so pretty much all there now. All right. Okay. All I need really is a nice cup of tea, then I'll feel much better. Okay, so here's my nice cup of tea. Let's show you that. Okay. And today's video is sponsored by PG Tips. That's a joke. All right. Oh man. Okay, now, so back to where we were. All right, so we're talking about half equivalence. Now I just want to formalize that for you guys, all right? So half equivalence, okay, let's talk about it. So when you do a titration, when you've got equal numbers of acid and base, moles, stoichiometrically equivalent, you see, you know, traditionally a color change. We call that the equivalence point. So when moles of acid equals moles of base, we got the equivalence point. You know, that's when we see a change of color in a standard titration. Okay, so they're equal numbers. Okay, so at full equivalence, equal numbers of acid and base. So therefore, half equivalence if you're adding base to acid, say, you've added enough base to get rid of half of the acid, okay? You've used up half original material. So, okay, so if you've used up half, you've got half left. If I put that in terms of a quick equation, okay, so I have HA in equilibrium with H plus and A minus. If you start removing the H plus by adding OH minus, okay, initially you got 100 here. You do it until you move 50 over, and you got 0 of these still, but you got still in equilibrium, of course. You now got 50 of those. These are keep continually being removed, right? Okay, so 50 and 50, equal amounts, half equivalents. Bottom line is equal amounts of A minus and HA. Okay, so you've got equal amounts of A minus and HA after you've added half enough titrant to get rid of half of the amount of stuff you're titrating. All right, so if we look at the Henderson-Hasselbalch equation, pH is pKa plus log A minus over HA. Because these are equal numbers at half equivalents, okay, so what happens at half equivalents, 50 and 50, whatever it is, that tends to 1, so log of 1 is 0. Okay, so therefore pH equals pKa plus log 1, this equals pKa plus 0, therefore pH equals pKa at half equivalents. Okay, so halfway along that buffer region is when you've added half the amount to get rid of all the material, so pH equals pKa if you remember that slide from before. Okay, so that's a little bit more detail on that. Now, let's do a true kind of biochemist's kind of dream question, right? So in your blood you have a buffer, and in pretty much all kind of mammalian systems it's the same buffer, okay? It's the carbonate buffer, or I should say, to be specific, the hydrogen carbonate buffer. All right. Now, blood has a regulated or pH controlled buffer of 7.4. Okay. So the buffer that does that is the carbonic acid hydrogen carbonate buffer. Okay. So that's the buffer in your blood. Okay. That controls the pH in your body essentially. Okay, so let's read this question. This group works. If you want to pause it and try it, give it a shot. It's kind of a harder question because it's designed for group work. Okay, so if you can solve this one, you're in real good shape. All right, but let's go through it. Let's read the question. So if the carbonic acid has a concentration of 0.0012, and these are actual real numbers. Okay, that's the concentration of carbonic acid in your blood. What is the hydrogen carbonate concentration in blood? Given that the Ka for the system is 4.3 times 10 to the minus 7. Then we can kind of look at the ratio of these two things and say, hey, what's blood better at resisting H plus or OH minus? Okay, so we're also given this information up here. The pH of blood is slightly different at body temperature. I think it's 7.1 or something. It's just that this is kind of standard temperature. Okay, so we have, well, we're going to use the Henderson-Hasselbalch equation, right? So we need pH, pKa. You could do a grid too, right? But Henderson-Hasselbalch for buffers is usually the best method. Okay. All right. So pH, pKa, and dissociated acid and conjugate base. All right. So pH is in the question, 7.4. pKa, well, it's kind of in the question. Ka is given, so pK is minus log of 4.3 times 10 minus 7, which equals 6.4. HA tells us right there, 0.0012. And we got to figure out the conjugate base concentration. So it's kind of a weird question. It's kind of a backwards question, if that makes any sense. Okay. There's a lot of work here, so I kind of divide the page into two, kind of in my head, and we'll get going on it. So, Henderson-Hasselbalch, pH equals pKa plus log A minus over HA. Careful, because I corrected that sign, right? When we move things around, it's actually a plus, right? So that's the correct version of the equation when pH is the subject. All right. Put in what we've got. I like to kind of put things in as we get them, right? So pH 7.4. You can do like a true algebra thing and put numbers at the end if you want. pKa 6.4 plus log A minus is what we want over HA, right? We'll deal with that in a minute. Okay, we'll put that number in a minute. Okay, therefore 7.4 minus 6.4 equals log of A minus over HA. You'll see why I didn't address this yet in a moment. Okay, 1.0 equals log, well, make sure you can see, A minus over HA. Now I'll take it back up here, right? Okay. Therefore, 1.0 equals, I can do that whole thing where, hey, divide logs is log subtracted, right? Okay, so therefore, log of two things divided is the log of this minus the log of that. Minus log HA. Fair enough. Therefore, one point oh equals log A minus minus the log of 0, 0, 1, 2. 1.0 equals log of A minus 0.0012 log, 0.012 log. Minus 2.92. Okay, rearrange it. And this is our destination. So log A minus, just bring this over, equals 1.0 plus, oh, make sure I do this right. No, that's a minus. Make sure I get my signs right. Okay, so that turns that into a plus 2 point. Let me get this straight. So the log of 0.0012 is minus 2.92, and I'm subtracting, and minus times a minus is a plus. Okay, 1.0 equals log A minus plus 2.92. Therefore, log A, yeah, sorry, let me just recap. A minus times a minus is a plus. 1 equals log A minus plus 2.92. Minus times a minus is plus. 1.0 minus 2.92, which equals minus 1.92. Okay, therefore, log A minus equals 1.92 negative. Do the 10 thing. A minus equals 10 to the minus 1.92, 0.012 molar. Interesting. So that's the final answer. The concentration of the conjugate is 0.012. The concentration, I'm going to write it over here, 0.012. So that's times 10 bigger than the concentration of the acid. Now if you think about it, okay, when you add acid to this equilibrium, okay, from an external source, it goes that way. So the more hydrogen carbonate in the tank, the better it is at resisting changes and adding H+, okay, which makes total sense. If I go the other way and add OH-, I'm removing H+, right? Okay, let me just go over that again. Let me just go. I got it wrong, didn't I? Okay, we'll go over that again. So if I'm adding H plus, the equilibrium is going to shift that way, right? Okay, because I'm going to use this to get rid of that. Okay, so in that case, if I have a large amount of conjugate base, I'm going to be better at resisting changes in adding H plus. All right, let's give it the glass half full, glass half empty argument. If I add OH minus, I'm going to remove H plus and we'll go that way. Okay, so I have large amounts, so this will be preferable. So if I'm adding OH to my buffer, I need large amounts of acid. If I'm adding H plus, I need large amounts of conjugate base. What do we have more of? Conjugate base. So it's better at resisting changes in H plus. Okay, which makes total sense because most of the nasty things out there in nature that sting you inject you with H plus. So our blood is designed to resist changes in adding H plus. All right. So again, this is going to be, available in the note packet, which I'll add as a downloadable PDF. Okay, so take a look at that in your own time. Now, more about drugs. All right, now, if you remember, we've talked about two different kinds of acid. There's the standard Arrhenius, right, and that's true for all acids and bases. So every kind of acid and base truly is an Arrhenius, which is just basically it increases the H plus if it's an acid and increases OH minus if it's a base. Increases those ions in solution. Okay. Then we had Bronsted-Lowry. Bronsted-Lowry are proton donors, which are acids, and proton acceptors, which are bases. So that's the proton transfer model. Okay. But think about the glass half empty, glass half full thing. If I'm thinking about something simple like water, all right, we can go with a pseudo, well, it's not a pseudo, it's actual Lewis structure, right? So if I'm donating an H plus from, say, HCl, it comes and sticks on here, doesn't it, right? And that thing makes the hydronium ion, okay? So the hydronium ion is made through water accepting a proton. It's a Bronsted-Lowry base, it accepts a proton. But if you want to think about glass half empty, glass half full, if you look here, oxygen, if you like, has donated a lone pair to that proton, right? So this oxygen is a hydrogen plus ion acceptor, or if you like, a lone pair donor. So glass half empty, glass half full. That's the Lewis model. The Lewis model concentrates on the behavior of the lone pairs, okay, which is great when we think about certain molecules which act as technically Lewis acids and bases, even though there's no H plus involved a lot of time. Okay, so Lewis acid are lone pair acceptors, and the Lewis base, and this is the base, is a lone pair donor. Okay, so when the hydrogen comes along, think of this as donating lone pair. It's a base. Okay, so it's kind of the same idea as you saw before with proton transfer, but just viewed from a different point of view. Okay, so there's ammonia, for example, so let's do NH3. So NH3, anything with a lone pair will do this, and all those interesting drugs out there have lone pairs, right? Okay, so here we have water and ammonia. Okay, we turn into NH4, so this will jump on here, so we get NH4. Put lone pair there, maybe. Plus OH minus. There we go. All right. Question. Kind of mentioned it already. Why do we worry about this even? It's the same thing as Bronsted-Lowry, right? Just from a different point of view. Hey, proton donor, lone pair donor. What's the difference, right? Well, as I mentioned, it turns out that most interesting molecules have nitrogen, right? Nitrogen has lone pairs, so they have this Lewis base behavior, right? So think of a Lewis base of anything with ammonia, sorry, anything with a nitrogen, which will have a lone pair. That has some interesting chemistry. All right. Now, we are going to talk about drugs of all different kinds here. Okay. Now, when we talk about drugs as chemists, we're doing it from a strictly kind of academic perspective. It's a bit like a trip to the restricted area of the library in Harry Potter, right? Okay, no one here is Tom Riddle. We're not going there for a bad reason. We're going there for, like Harry did, for an academic reason. Okay, the nerd in me says, why? Because he just goes up there with his, his invisible cloak and gets in, right? Avoids the guy with the cat, right? And so my question is, why don't they just put a lock on on the restricted area? Because he just walks in. And I think to myself, oh, but Hermione, she can pick locks with her magic spell. And then I think to myself, well, why don't they just put an enchantment on the lock? I'm just such a nerd. Anyway, so this is the restricted area of the library. We're going to talk about legal drugs and illegal drugs, but the bottom line is they're all just interesting molecules to us chemists. So we are going to visit the restricted area of the library for academic reasons. Okay, now when we think about that, back in the 1980s, there was this kind of legendary nightclub in New York. I think it was called Studio 52 or something. And everybody at this nightclub was doing like drugs in the bathroom. It was just this notorious place. And when you look back in the 80s and the early 90s, and you talk about people who were basically doing cocaine in the bathroom and heroin and things like that, they talked about freebasing. So that's a verb, to freebase, right? What the heck are they talking about? What's a freebase? Well, that's actually the pure molecule. The pure molecule has nitrogens on it, which are Lewis bases. Okay, so the free base is just the pure molecule, essentially, right? So it turns out that free bases are volatile and they tend to fall apart very easily. They decompose. So, they do all these kind of weird and wonderful things to get them into their bodies, right? Back in the day, right? And that's where the term free basing came from. All right. Now, it turns out these days we have the power of science. And to be honest, you can turn these old school opiates and things like that into much more potent drugs by turning them into acid salts. Okay, so the bottom line is most free bases are volatile and not soluble in water. That's the key thing. Remember we talked about solubility? If you can make a drug soluble, you can take it as a tablet. You can't take cocaine or heroin as a tablet, right? You see these shows where they're snorting it and they're chasing dragons, all that business. Again, restricted area of the library, right? Okay. So these are not, in the pure form, cocaine and heroin cannot be ingested, right? They have to be somehow get into your body in a different way, okay? So because they don't dissolve in water, you just can't eat them. You can't take them as like oral medication. So to do that, how do you turn a free base into an oral medication? How do you make it soluble? Well, this is how we do it. We turn it into what's called an acid salt, okay? And this is really the foundation, and I'm going to go off on a bit of a rant over the next page or two. This is the foundation of the opioid crisis. What do? You take a drug like heroin, you modify its structure slightly, and it becomes 100 times more potent. You call that stuff fentanyl, right? And then you take that fentanyl and you turn it into a shelf-stable salt, which can be taken orally, and then you have an opioid crisis, right? Big Pharma, thank you so much. Now, so here we go. What is an acid salt? Okay, an acid salt, there's your drug of choice. It can be cocaine, it can be heroin, it can be fentanyl, whatever it is, right? Because it's got a lone pair on it, you react that with HCl, hence acid salt. This H plus will just jump on this lone pair and make an ion. It will stick to the other ion to make a salt. All salts dissolve in water pretty much, so that's soluble. You can now take that as an oral medication, okay? And that's the origin of the opioid crisis, right? I shouldn't really say that exclusively, because pretty much all drugs are available as acid salts because they're stable, they can dissolve in water, so you can take them as tablets, right? So there's a couple of other classics. You name it, you've probably ingested it as an acid salt, right? So here's Levitra, which is an erectile dysfunction medication. I'm not being sponsored to say that. That's a joke, okay? All right. So that's an erectile dysfunction medication, and they have the drug name with HCl written on the back. So that tells you it's soluble in water, right? That's a legal drug, right? Maybe you heard of crack cocaine, the epidemic of crack cocaine in the 80s and 90s, right? People talk about baking it, right? So you take sodium hydrogen carbonate, and academic reason only, right? Let's go back over here first. So how do I make Levitra? So here's my Levitra molecule with its lone pair. I take my HCl, that jumps on, turns into Levitra H plus, Cl minus, that's a salt. So that's now an oral medication. Crack cocaine, they say it's instantly addictive. I don't know. Hopefully you never have to interact with this stuff. But there's cocaine, okay? and you bake it in your kitchen with baking powder. It's just so easy to make. It's, you know, restricted area of the library. Turns into, you make a mixed salt, right? So you make this guy here, which is plus, and then the sodium carbonate. It might be the other way around, but there it is. It's a minus sign. Okay, so that's called a rock. That's a rock. It's a crystalline material that's soluble in water. Right. Okay. So, you know, people that smoke crack, they're basically vaporizing it, and then when it gets into your lungs, it dissolves through the lining of your lungs. All right. Now, got a bit of a rant here. So, the opioid crisis, Levitra, you know, Big Pharma is, in my opinion, and you know, take it for what it's worth, Big Pharma's a blessing and a curse because they provide us with all these drugs, but are they providing us the right drugs, right? You know, if we spend as much money as we spend on, you know, giving middle-aged men erections and hair, right? That's the main funding for drugs, is erections and hair, right? We probably have solved cancer by now, okay? So, you know, as organic chemists, you know, you come through and you think, oh, I'm going to change the world, I'm going to create the next, you know, well, the cure for cancer, and then you end up working for a company and you ended up on the Boner Pill project, okay? It's a bit like Bernadette from The Big Bang Theory, if you watch that show, because they talk about it, right? Okay, not just me. All right, so that's that. All right, now, the next topic, okay, the next topic, and I forgot to start my timer, all right. Next topic is solubility, equilibria. So, you know, when we have a solid dissolving in water. So what I'll actually do, I'll actually stop there because I'm not sure when I'm going to run out of time. And then we'll have one more video which has just the remaining few pages. Okay, so we'll stop there. All right, hopefully the last video for the packet. Talking about solubility, now things dissolving in other words, so solids dissolving to make solutions, okay? Now there's a picture of a cup of tea, and I think I've told you this example before when we talked about saturated solutions. Talk about my brother, right? So my brother back in the day used to have 13 sugars in his cup of tea, and you get to about 6 and then no more dissolves, and that's a saturated solution, right? Fair enough. Now, you can pretty much make a saturated solution about anything. You get to the point where it doesn't dissolve anymore. Fair enough, right? So we talked about saturated solutions before. For sugar, you can actually dissolve quite a lot of stuff in there. Salt, table salt, lots of stuff dissolves before it gets saturated. But what about things like chalk? If you look in solubility charts and things like that, chalk is insoluble. Silver chloride, classic, insoluble, right? But no, remember everything's in equilibrium. Remember, there is no such thing as a non-reaction or a complete reaction. Everything's in equilibrium. It's just that this is dissolved to such a small an extent, we hardly ever bother with it, right? But if we do want to bother with it, we'll get into this equilibrium math we're going to talk about now, okay? So things that are apparently insoluble, like chalk, are actually what we call sparingly soluble. A little tiny amount goes into solution. So if I had some calcium carbonate, put it in a beaker with some water, I'd have a small amount of calcium and a small amount of carbonate go into solution and then get into an equilibrium, right? Even though the amount is tiny, it does reach a maximum amount, a small yet limiting amount, right? So at that point, it's technically a saturated solution. So it's saturated with a very low concentration of ions in solution. Okay, so because they're in equilibrium, and at that point of saturation, it's kind of a fixed number, constant time, right? So the equilibrium constant is calcium carbonate. That's my 2 ions in solution. If I'm doing this technically in terms of formulas and things, divided by the calcium carbonate. Now, if you remember from the good old days when we did heterogeneous equilibrium, these guys have measurable concentrations. This is a solid, it does not, right? So we can say, hey, K times calcium carbonate concentration equals a new constant, which we call solubility product, which equals calcium 2 plus carbonate minus. Okay, so same kind of thing. We're going to kind of multiply the constants out. and we get what's called a solubility constant. Okay, it's just basically the ions in solutions, because the solid doesn't count in any equilibrium expression. Okay, it doesn't have a measurable concentration. So any sparingly soluble salt ionic compound will have a relevant or related KSP. Okay, numbers are always small. All right, remember the line in the sand for solubility. Well, sorry, let me back up. The line in the sand for a reaction or not reaction was 10 to the minus 6, right? Okay, think of that as an equilibrium number, right? So here we've got 10 to the minus 9. Yeah, it's 1,000 times less than the threshold for a reaction. It happens, just not in very large amounts at all. Okay, so it is a measurable but small amount. It's called a solubility product because it's this one times this one, a product, and what's called solubility, which we'll get to later, is technically defined as the concentration of the metal ion in solution. Okay, so this times this, solubility product, and it's a fixed number, it's a constant. All right, so since we are dealing with sparingly soluble materials, okay, the KSPs are necessarily low. Okay, now you may you may recognize a couple of things which we in Chemistry 101 defined as insoluble. In our solubility chart, AgCl was defined as a solid. Why? Because its KSP is super small, right? On the other hand, Ag2SO4 was designed as soluble. Its KSP is above that -6 threshold, right? So that was aqueous before, and that was a solid before. But remember, that's all relative. They all dissolve to some degree as defined by the KSP. All right? The smaller the KSP, the less they dissolve. All right? So we can write solubility expressions for these things, just like we did with the calcium carbonate. All right? So it's always a good idea to write the equilibrium first. Barium +2, sulfate -2. In equilibrium, Ba2 plus SO4 2 minus. You know, there it is right there. So we actually have a value we can stick on in a minute. Therefore, KSP, products over reactants, reactants we forget about, which equals that number, 5.0 times 10 to the minus 9. Okay, nice place to pause. Pause, give the remainder a go. Okay, remember this is careful with these because they have more than one ion. Okay, so give it a pause, give it a go, and I'll catch you up. All right, next one, calcium fluoride in equilibrium with calcium ions and 2 fluoride ions. Careful, we're going to have that whole power thing. So KSP, products over reactants, forget about the products because they're solid. One of those, same rules apply. Same rules apply. All right, which equals a number 3.9 times 10 minus 11. All right. Finally, silver sulfate, Ag2SO4. Careful, 2Ag plus, SO4 2 minus, Ag plus squared, SO4 2 minus, which equals a number, it's 2 Ags, -5, below the -6 threshold, so we generally say, you know, before, oh, that's soluble, but it's very, very sparingly soluble. Okay, so as with other equilibria, we raise the concentration to the power of the stoichiometric constant. Okay, so hopefully writing those is not so bad. Okay, they are mathematical relationships, so we can do some interesting math. Okay, so try this by yourself. Okay, hopefully you can work it through given the, let me just give you the expression here. It's the one we saw earlier. So an easier one to start, just two things dissolving, and the number was 4.96 times 10 to the minus 9 from previously. Okay, so question says, you drop a stick of chalk, calcium carbonate. Now this is a heterogeneous equilibrium, so the chalk has to go in before the equilibrium can establish, of course. Okay, then it gets into a saturated solution with low concentrations. Okay, that's the KSP situation. Okay, so you drop a stick of chalk into some water. What will the concentration of calcium ions be in the resulting saturated solution? Okay, after we got to equilibrium. Okay, so equilibrium establishes when we got saturation. All right, so let's think about it. Since 4.96 times 10 to the minus 9 equals Ca2 plus times CO3 2 minus. And because this is in a 1-to-1 ratio, concentration of this guy, we call it X, is the concentration of that guy because it's in a 1-to-1 ratio, right? We don't know how much goes into solution, all right? So therefore, this number equals X squared. 4.96 times 10 to the minus 9 equals X squared. Therefore, X equals the square root of 4.96 times 10 minus 9. 6.7 times 10 to the minus 5. Okay. So again, it's a... Could we do a grid for this? We could, but it's at the point now where, you know, there's no reactant, so the grid isn't really necessary. Okay. Now, we get interesting questions when we combine pH with sparingly soluble materials. All right, so let's look at this one. Okay, now it's a harder example, and I do like to put this on tests. Hint, hint. Right. Okay, so we have magnesium hydroxide, MgOH2 solid. It's going to get into solution. Right, now be careful because you're going to get Mg2 plus 2OH minus. Right, there's 2 in there. Okay. Now, because we've got OH, that we can get to POH and then pH, right? Okay. So this one, a saturated solution of magnesium hydroxide has a pH 10.17. If we think about it, we get one of these and two of these through the dissociation, right? So if that's X, that's 2X, right? Okay, now if you've got pH, we can go to POH. If we've got POH, you can find the OH minus ion concentration. And because that divided by 2 is the magnesium, we can find the magnesium ion concentration. Okay, so saturated solution of magnesium hydroxide has a pH of this. Find KSP. KSP is going to be what? Be careful. KSP equals magnesium times hydroxide squared. Careful, which equals X times 2X squared, 4X cubed. Alright, so KSP is 4X cubed. So solve for X and then 4X cubed. Alright, pause there, try it. Okay, and then I'll do it. Okay. So pH plus POH equals 14, therefore POH equals 14 minus 10.17, which equals 3.83. Therefore, OH, do that reverse math, 10 to the minus POH, 10 to the minus 3.83, 1.48 times 10 to the minus 4. Okay, so that's OH minus ion concentration, divide by 2, therefore, to find X, which equals 1.48 times 10 to the minus 4 over 2, 7.4 times 10 to the minus 5, therefore KSP 4x cubed equals 4 times 7.4 times 10 to the minus 5 cubed 1.62. Oh, sorry, bring it up. 1.62 10 to the minus 12. All right, so it's a tiny number, but you expect tiny numbers for solubility products, don't you? Okay. All right, so given the pH of a sparingly soluble salt that features an OH minus ion, you can find KSP. Okay, and that's a favorite for tests, so beware of that. Okay. Now, as I mentioned, solubility is generally speaking the concentration of the metal only. Okay, so the solubility of any sparingly salt is expressed in terms of the metal ion. This comes from industry, because in an industry they're always interested in separating out these ions, you know, and then making the metal. So you might pull out some sodium, some silver. Sorry, you wouldn't pull out sodium; that would be too soluble. Silver, lead, things like that. So when you're refining metals, which generally have compounds of low solubility, this is super important. Okay, so solubility, which we just call it S, equals the concentration of the metal ion. Okay, and in this case, because it's 1 to 1, it's also the concentration of the counter ion. Okay, so if you want KSP in terms of S, it's nice and easy, very simple. Okay, so KSP equals, this is S times same number S. Oh, I'm just doing it again, right? Okay. KSP, solubility of silver times the same number, solubility of silver again, because it's the same number, 1 to 1, which equals S squared. So therefore, if you want solubility by itself, it's just the square root of KSP. All right. Now, that gets a little complicated when we look at things with multiple products, for example. Okay, so determine KSP and solubility expressions for the following. Okay, so here solubility of the metal is S, so that, because there's two of them, is 2S, right? So therefore KSP equals calcium 2 plus fluoride minus squared, because there's two of them, which equals S, and that's 2S, and that's squared, which is 4S cubed. Okay, so KSP 4S cubed. All right, if I rearrange all that, make S the subject, you can do this by yourself. S is KSP over 4 cube rooted. All right, next one. What's the calcium fluoride solubility? Okay, S in other words. Okay, and let's do this. So when we look at this one, okay, what's the solubility? That's S, that's the concentration of calcium. Okay, so when it says that, we're really solving for the concentration of calcium. Okay, find S, it's the concentration of calcium from KSP. So when we think about it, we're just going to use that equation. S equals the cube root of KSP over 4. Well, that's easy, right? 3.9 times 10 to the minus 11 over 4 cube root, which equals 2.1 times 10 to the minus 4 molar. Okay, fair enough. That wasn't so bad. Now, so that's the solubility of calcium, right? Calcium ions. Okay. Now, in industry, they don't usually do things in moles per liter. That's what we do in chemistry. Okay, so in the biochemical and the industrial fields, it's usually grams per liter or milligrams per milliliter. Okay, so how do we turn this into what they want? Okay, grams per liter. All right, it's actually simpler than you think. If you remember back to Chemistry 101 and we did that ppm calculation, very similar, right? Okay, so 2.1 times 10 to the minus 4 moles per liter, and we're going to turn that into grams per liter. So all we're doing is turning moles to grams, right? How do you turn moles to grams? Well, you multiply by molecular weight. What's the molecular weight of calcium fluoride? It's actually 78.1 grams per mole. Okay, so (1.6 times 10 to the minus 2 grams per liter). Okay, so be careful there. Okay, think about a chain conversion. It's a bit like a ppm conversion. Okay, and this is more popular in fields such as, you know, industrial chemistry and biomedicine and things like that. All right. Next one, you can apply, of course, common ion to this. It is an equilibrium. Okay, so you can throw a common ion in and you get what's called selective precipitation, which is super important in industry. All right, so it's kind of a tricky one to get the hang of, but once you do, it's, you know, it's pretty straightforward. Okay, so we can modify the solubility of a specific ion in a mixture by playing with this math. Okay, and then, hey, we can selectively precipitate it from a mixture if that's the case. All right, so calculate the molar solubility of calcium fluoride. So really it's the concentration of calcium 2+ in a solution that's 0.1 calcium nitrate. So remember, all nitrates are soluble. So I'm going to have a 0.01 calcium ion as a, yeah, you guessed it, common ion, right? So I'm going to use a modified ICE grid. So that's the trick. So I'm going to use a modified grid. Okay, this is how it works. Okay, we're going to throw a little pellet of calcium fluoride into a beaker that's already calcium 2+ aqueous in solution at 0.01 strength. Okay, and then an equilibrium will set up between the calcium fluoride and the solution, but the amount of calcium going into solution will be diminished because it's going to be competing against, if you wish, the calcium that's already there. Okay, so let's look at this. So calcium fluoride, equilibrium with calcium 2+ plus 2F minus. Okay, ICE. Initially, obviously it's a solid, it doesn't really apply. This is the common ion, and initially none. Change, we're going to make, normally we write an X here, don't we? Normally we write an X here. But hey, in terms of our algebra, it's an S, isn't it? And that's 2S. All right. At equilibrium, we have 0.010 plus S and 2S. All right. You can make the weak acid approximation. That's an even smaller concentration, right? Okay. So, KSP, don't lose sight of our prize here, right? Calculate molar solubility, that's S. Yeah. Okay. So KSP equals calcium 2+ fluoride minus squared, which equals approximately 0.01 times 2S squared, KSP, should have the number somewhere. Okay, oh yeah, it's in the previous table. Flip back, it's in the table. We got it, there it is. Okay, so basically we're going to solve for S, yeah? So 3.9 times 10 to the minus 11 divided by 0.01. Multiply that, that's out, that's 4S squared, isn't it? So it's going to be divided by 4 square root equals S, which equals 3.1 times 10 to the minus 5 moles per liter. Okay. Just double check. Yep, 3.1 times 10 to the minus 5. All right. Now, this whole process is kind of interesting, okay? Because if you ever work in a lab, if you have a real hard time dissolving something, oftentimes you'll add an acid to it and it will dissolve really well in the acid but won't dissolve in regular water. Okay, now this is a common ion effect again. Okay, now this is a little bit morbid, but that's that's Jeffrey Dahmer, right? He's well, he was, because he's dead now, right? He was killed in the jail in Milwaukee, right? Okay, so infamous serial killer Jeffrey Dahmer, right? So what he would do, it's kind of crazy, he would kind of go to these nightclubs and pick up guys and take them back to his place, and then he'd turn them into these kind of zombies by kind of dripping kind of acid onto their skulls and things. It's totally crazy, right? And then he never got caught for such a long time because they used to dissolve their bodies, right? If you want to find somebody and charge someone with a crime like murder, you need to have a body, really. And Jeffrey used to dissolve their bodies, right? The skin and flesh and stuff's easy to dissolve, but the bones, how do you dissolve bones? Well, calcium phosphate's a bit like magnesium carbonate, okay? So we'll talk about that example, right? Jeffrey Dahmer actually was caught because they raided his house and they couldn't find any bones. And then they, you can look this up on the internet. They looked in his fridge and found a few heads. So don't, if you don't keep heads in your fridge. Okay. So consider this equilibrium, right? So there's a sparingly soluble material that could be calcium phosphate bone, right? Same idea. And it's in equilibrium with its solvated ions in very small amounts. It's a solubility product situation. However, let's say now we use HCl as a solvent, right? It completely breaks apart, right? But then H plus will react with one of the products from dissolution to make HCO3, right? So it's a bit like a buffer. It's actually going to remove stuff from solution. So if I have Mg CO3 solid in equilibrium with Mg2 plus CO3 2 minus, and I throw some H plus at it, and this works for pretty much any insoluble thing, right? That turns into HCO3 minus. That's a different thing, so that goes down, right? That means to replace this, the equilibrium moves to the right. So we can dissolve our insoluble things by adding acid to them, okay? All right, because the conjugate product, oh wow, let's not call it the conjugate, one of the solubility product over here reacts with the external H plus to make something new. If it's new, it's not an equilibrium anymore. Right? Okay, last page. Now this one, I'm not going to go through it now. Okay, I'm not going to go through it now. I am going to set it for some significant extra credit homework. Okay, I'll give you a couple of clues though. Okay, so a solution can, this is what they do in industry. So in industry, you'll like refine some ore and you'll typically add nitric acid to it, and everything will dissolve, right? So you've got some Pb2 plus ions in there and some silver ions in there, okay? AgI has a KSP of 10 to the minus 17, lead iodide 10 to the minus 9, right? So what you're gonna do, you're gonna drip in I minus aqueous, yeah? When the solubility product is reached, right, precipitation will happen. So what's gonna precipitate first? This one or this one? Well, obviously this one, right? Because the concentration of the ions to get to 10 to the minus 17, it's going to be a very small amount of I minus you add. You've got to add a lot more iodide to make this one precipitate when this is true, right? Okay, so this one will go first and this one will go second, okay? That's easy. Now, to prove it, you got to do the math, right? So work out the specific concentration of I minus needed to begin precipitation, all right? So if you can do it for both. Do it for AgI, which is an easier problem, okay? But really you should do it for PbI too, okay? So work out the concentration of I minus, set up an ICE grid, okay? Two different solubility product values for KSP. And then tell me what value I minus has to be for KSP to be reached, right? And when that happens, you get a solid, okay? So obviously this one will happen first. You have a lower concentration of I minus to make that happen. And then this one will happen second, okay? So, work it through here, take a picture with your phone, send it to me as an email attachment, okay? And that's the end of the packet, all right.